On August 25th, 2012, at a distance of exactly 121, 6 astronomical units from the Sun, a 40-year-old spacecraft traveling at over 38,000 miles per hour crossed an invisible line in space that no human-made object had ever crossed before. Its instruments recorded something that, according to every model scientists had built up until that moment, should not have been possible. The density of charged particles around the spacecraft didn't just change, it spiked. Then, months later, it spiked again. And again. By the time researchers had gathered enough data to be certain of what they were seeing, they realized the plasma density outside our solar system was not behaving the way physics said it should. It kept rising, long after it should have leveled off. Temperatures in that same region were measured between 30,000 and 50,000 Kelvin, hot enough to vaporize solid metal in an instant under normal conditions. And yet the spacecraft passed through it completely unharmed. This is the story of Voyager 1, the far edge of our solar system, and a discovery so strange that scientists spent years triple-checking their own data, because they didn't quite believe what it was telling them. To understand why this matters, you have to go back to 1977, a year when the world was still trying to process what it meant to send machines beyond the reach of Earth. NASA had a narrow window, a once-in-175-year alignment of the outer planets that would let a single spacecraft use the gravity of Jupiter, Saturn, Uranus, and Neptune like a series of slingshots, picking up speed at each pass and flinging itself further into the dark. 2 identical probes were built for this journey. Voyager 2 launched first on August 20th. Voyager 1 followed on September 5th, but because of a faster trajectory, it would overtake its twin and become the more distant traveler. Neither spacecraft carried more computing power than a modern calculator. Neither was expected to survive more than 5 years. Both are still transmitting data back to Earth today, decades after anyone thought that would be possible, from a distance so vast that their radio signals, moving at the speed of light, take more than 22 hours to reach us. For the first few decades of its journey, Voyager 1 did exactly what it was built to do. It flew past Jupiter and sent back the first close images of the Great Red Spot in staggering detail. It discovered active volcanoes on the Moon, Io, the first confirmed volcanic activity anywhere in the solar system outside Earth. It swept past Saturn and captured the intricate braided structure of its rings, then used that flyby to bend its trajectory sharply upward, out of the plane in which the planets orbit, sacrificing any chance of visiting Uranus or Neptune in exchange for a close look at Saturn's massive moon titan. From that point on, Voyager 1 was no longer a planetary explorer. It was headed somewhere else entirely, somewhere no spacecraft had ever gone, toward the outer edge of the Sun's influence, and eventually out of the solar system altogether. The Sun does not simply stop mattering at some fixed boundary the way a country's border does on a map. It projects its influence outward in the form of the solar wind, a continuous stream of charged particles, mostly protons and electrons, blasting outward from the Sun's corona in every direction at speeds that can exceed 1,000,000 miles per hour. This wind inflates a vast bubble around our entire solar system called the heliosphere. Inside that bubble, the Sun is the dominant force, shielding the planets from the harsher radiation and cosmic rays that fill the rest of the galaxy. But the solar wind doesn't blow forever. As it travels outward, it thins out, loses pressure, and eventually reaches a point where it can no longer push back against the material drifting between the stars, the interstellar medium. That boundary, where the outward pressure of the solar wind finally equals the inward pressure of interstellar space, is called the heliopause. It is, in the most literal sense, the edge of the Sun's kingdom. For decades, this boundary existed only in theory. Scientists had modeled it, estimated its distance, and argued about its shape, but no instrument had ever measured it directly, because nothing built by humans had ever traveled far enough to reach it. Voyager 1 changed that. As it approached the outer reaches of the heliosphere through the late 2000s and into the 2010s, its instruments began registering strange signs. The intensity of solar particles around it started dropping. The count of galactic cosmic rays, high-energy particles from outside the solar system that are normally deflected by the Sun's magnetic field, started climbing. These were the first hints that something fundamental was shifting around the spacecraft, that it was leaving one region of space and entering another. Then, on that day in August 2012, the transition became undeniable. The count of cosmic rays from beyond the solar system jumped by a factor of nearly 3 in a matter of days. At the same time, the count of particles originating from the Sun itself collapsed to almost nothing. Scientists watching the data in real time described it as watching a door slam shut behind the spacecraft. But here is the part that made researchers hesitate before declaring victory. One of Voyager 1's key instruments, the one specifically designed to measure the direction and strength of the surrounding plasma, had stopped working decades earlier, in 1980, after a mechanical failure. Without it, the team couldn't directly confirm they had crossed into a region with different plasma properties. They had indirect evidence, dramatic and compelling evidence, but not the smoking gun. For months, the announcement was held back. Scientists debated internally, ran the numbers again, argued about whether what they were seeing could still be explained as some kind of temporary anomaly within the solar system rather than a genuine crossing into interstellar space. The confirmation, when it finally came, arrived almost by accident, and it is one of the more remarkable pieces of detective work in the history of space exploration. In March 2013, a massive eruption from the Sun, a coronal mass ejection, sent a shockwave rippling outward through the solar system. It took about 13 months to reach Voyager 1's location, arriving in April of that year. When that shockwave hit the plasma surrounding the spacecraft, it caused the plasma to oscillate, to ring like a bell, and Voyager 1's plasma wave instrument, which was still functioning even though its plasma direction sensor was not, picked up that ringing. From the pitch of those oscillations, scientists could calculate the density of the plasma around the spacecraft for the first time with real precision. The number came back at roughly 0. 8 particles per cubic centimeter. That was roughly 40 times denser than the plasma inside the heliosphere and remarkably close to the density scientists had long predicted for true interstellar space. It was the confirmation they needed. Voyager 1 had not just brushed against the edge of the solar system. It had passed through it back in August 2012 and had been sailing through interstellar space for months without anyone being able to prove it. This alone would have been one of the great discoveries in the history of space science. The first direct, in-place measurement of the true interstellar medium, the material that fills the vast space between stars. But it is what happened next in the years that followed that turned this from a remarkable milestone into something scientists still struggle to fully explain. Because once researchers had a reliable way to measure plasma density using these oscillation events, they started tracking it over time. And what they found broke the simple picture everyone had assumed. The expectation, based on decades of modeling, was straightforward. Once Voyager 1 crossed the heliopause and entered the undisturbed interstellar medium, the plasma density should settle into a relatively steady, uniform value. Interstellar space, after all, is supposed to be close to homogeneous, over the kind of distances a spacecraft could travel in a few years. Instead, the density kept climbing. By 2015, roughly 2.5 years after the crossing, the plasma density Voyager 1 was measuring had risen well beyond that initial 0. Reading, continuing an upward trend that, according to the standard models, simply should not have been happening. Some analyses found the density had increased by more than 50% from where it stood at the moment of crossing, and continued increasing further still as the spacecraft pushed deeper into interstellar space over the following years. This is where the word impossible starts to earn its place in the story, not in the sense of defying the laws of physics, but in the sense of defying every prediction built on the best understanding available at the time. Space beyond the heliopause was supposed to be a relatively calm, steady sea. Instead, Voyager 1 found something more like turbulent, rippling water, a region actively being shaped and compressed by forces nobody had fully mapped out. Scientists now believe part of what's happening is that the heliosphere itself, as it plows through the interstellar medium like the bow of a ship moving through water, is compressing the material just outside its boundary, creating a kind of pile-up effect, a region of higher density directly adjacent to the heliopause that thins out only gradually as you move further away. In other words, the very edge of our solar system's bubble might be pushing up a wave of denser material ahead of it, the same way a boat pushes water ahead of its hull, and Voyager 1 spent years driving straight through that wave without anyone anticipating it would be there in that form or to that degree. Layered on top of this density mystery is the temperature discovery, which is in some ways even harder to reconcile with intuition. Data gathered from the boundary region, incorporating measurements from both Voyager spacecraft as they approached and crossed the heliopause, revealed temperatures in the range of 30,000 to 50,000 Kelvin. To put that in perspective, the surface of the Sun itself is around 5,800 Kelvin. This means the material at the ragged edge of our solar system, a region most people would picture as a dark, frozen, empty void, is in some sense hotter than the surface of our own star. Researchers have taken to calling this thin, superheated boundary layer a wall of fire, not because it looks like flames, but because the plasma there has been heated to temperatures that would instantly destroy almost anything solid that lingered in it for long. The reason Voyager 1 wasn't torched by this wall of fire comes down to one crucial detail, and it's a detail worth sitting with, because it reveals something beautiful about how differently physics behaves at these scales. Temperature, in the everyday sense we experience it, is really a measure of how much energy individual particles carry, but heat, the thing that actually damages or destroys an object, depends on how many of those energetic particles are hitting you and how often. In the region Voyager 1 passed through, the particles are moving with enormous energy, which is what gives that hot temperature reading, but there are almost none of them. The density out there, even accounting for the mysterious increase scientists observed is still almost unimaginably sparse compared to anything on Earth, a near-perfect vacuum by any earthly standard. You could stand in a space with a temperature of 50,000 Kelvin, in theory, and not be burned at all, simply because there aren't enough particles present to transfer that thermal energy into you in any meaningful way. It's the difference between touching a single spark from a sparkler and standing in a bonfire. The energy per particle can be identical. It is not a clean, static wall. It's an active, dynamic, breathing structure, shaped by the push and pull between the sun's own 11-year activity cycle and the pressure of the interstellar medium pressing back from outside. When the sun is more active, its wind pushes harder, expanding the heliosphere outward. When solar activity dips, the boundary can contract. Shockwaves from solar eruptions, like the one that first allowed scientists to measure that initial plasma density in 2013, ripple all the way out to this boundary and beyond it, disturbing the plasma in the interstellar medium itself, sometimes for months at a time in patterns researchers are still working to fully map. What makes all of this even more remarkable is that Voyager 1 was never designed to make these measurements. It was built in the 1970s, engineered for a 5-year planetary tour, using instruments intended to study the atmospheres and magnetic fields of Jupiter and Saturn, not the exotic physics of the true interstellar frontier. And yet, nearly half a century later, this aging spacecraft, running on decaying plutonium and communicating through an antenna smaller than most household satellite dishes, became the tool that let humanity directly sample the space between the stars for the very first time. No telescope, no simulation, no theoretical model could substitute for what Voyager 1 actually touched with its own instruments as it crossed that threshold. The journey to confirm and understand all of this has not been quick or easy, and that slowness is in its own way part of what makes the science so trustworthy. Researchers involved in the mission have described the process of confirming the heliopause crossing as a painstaking one, checking and rechecking every signal, because a claim this significant, the first time any human-made object left the solar system, demanded an extraordinary level of certainty. It wasn't declared based on a single reading or a single dramatic spike. It was built from multiple independent lines of evidence pointing in the same direction: the collapse of solar particle counts, the jump in cosmic ray intensity, and eventually the direct plasma density measurement from the oscillation event more than a year later. Only when all of these pieces aligned did the team feel confident enough to make the announcement to the world. It's worth pausing here to appreciate just how far away this all happened. A distance of over 121 astronomical units means Voyager 1 was more than 121 times farther from the Sun than Earth is, translating to roughly 11 billion miles, or about 18 billion kilometers, at the moment it crossed the heliopause. Today, that distance has grown even further. Voyager 1 continues to move outward at roughly 38,000 miles per hour, meaning it covers a distance greater than the diameter of the Earth every few minutes. It is now the most distant human-made object in existence, farther from us than any spacecraft, any satellite, any piece of technology humanity has ever built or launched. A radio signal sent from Voyager 1 today takes nearly a full day to reach antennas on Earth, and by the time scientists receive it, the spacecraft itself has already moved on millions of miles further into the dark, into a region of the galaxy no human eye has ever directly observed and no human presence has ever touched. The scientific value of this journey goes far beyond satisfying curiosity about what lies beyond our solar neighborhood. Understanding the true boundary of the heliosphere and the properties of the interstellar medium just beyond it helps researchers understand how well our solar system is protected from the wider galaxy. The heliosphere functions in a sense like a protective bubble, deflecting a significant portion of the galactic cosmic rays that would otherwise bombard the inner solar system, including Earth. These cosmic rays are high-energy particles that can damage biological tissue and electronic systems alike. By measuring exactly how that shielding works at its outer edge, how dense the material is just outside it, how hot, how turbulent, scientists can build far more accurate models of how that protection might change over time, particularly as the sun's own activity cycles through periods of strength and weakness over the coming centuries. There's also a deeper significance tied to where this material outside the heliopause actually comes from. Researchers studying the very local interstellar medium, the small patch of space our solar system currently happens to be passing through, believe much of it originated from ancient supernova explosions, the violent deaths of massive stars that occurred long before our solar system even formed. In a very real sense, when Voyager 1's instruments sampled the plasma beyond the heliopause, they were sampling the scattered remnants of stellar explosions from the deep past, material that has drifted through the galaxy for millions of years before, happening to occupy the same patch of space our sun is currently moving through on its own orbit around the galactic center. Studying this material offers a kind of forensic window into the life and death of stars that existed long before Earth did. None of this diminishes the raw wonder of the situation, and if anything, it deepens it. Here's a spacecraft, launched during the era of disco and the first Star Wars film, built with technology so limited that a modern smartphone has many thousands of times more computing power. And it is still functioning, still transmitting, still making discoveries that upend the predictions of scientists armed with supercomputers and decades of accumulated data. Every one of Voyager 1's key instruments that remain operational today is doing so far beyond its original design lifetime, kept alive through careful power management as its radioisotope thermoelectric generator, the device that converts the heat from decaying plutonium-238 into electricity, slowly loses output year after year. Engineers on the mission have had to make increasingly difficult choices, shutting down instrument after instrument, deciding which scientific capabilities to sacrifice in order to keep the spacecraft's core systems and remaining instruments alive for a few more years. The plasma wave instrument responsible for that critical 2013 density measurement, remarkably, is one of the survivors, still listening to the whispers of interstellar plasma from over 10 billion miles away. This slow, deliberate shutdown process is a sobering reminder that Voyager 1's mission, however extraordinary, will eventually come to an end. Current projections suggest the spacecraft will likely lose the ability to power any scientific instruments sometime in the coming years, with total loss of communication expected sometime in the following decade, as the power supply continues its inevitable decline. When that day comes, Voyager 1 will not stop moving. It will continue drifting outward, silently forever, carrying with it the golden record, a phonograph disc containing greetings in dozens of languages, recordings of natural sounds from Earth, and a curated selection of music meant to represent something of what it means to be human, just in case. Against astronomical odds, it is ever encountered by another intelligent species in the unimaginably distant future. Voyager 1 is projected to pass within a couple of light years of another star, roughly 40,000 years from now, and after that, it will simply continue on, a silent wanderer, long after every trace of the civilization that built it has changed beyond recognition or vanished entirely. But before that silence falls, Voyager 1 has given us something extraordinary, a direct physical confirmation that the space just beyond our solar system's border behaves in ways nobody fully anticipated. The rising plasma density that shouldn't rise, the wall of superheated material that shouldn't exist so close to what should be a serene interstellar void. The realization that the heliopause isn't some clean, fixed boundary line, but a living, shifting frontier shaped by an ongoing tug-of-war between our sun and the rest of the galaxy. These findings have forced a genuine rewrite of the models scientists use to describe the outer solar system, models that will guide the next generation of missions, including proposed future interstellar probes designed from the outset to study this region with modern instruments, something Voyager's 1970s-era engineering was never built to do with full precision. It's also worth remembering that Voyager 1 does not travel this frontier alone. Its twin, Voyager 2, launched just weeks earlier, but following a longer, slower path through the outer planets, crossed its own heliopause boundary in November 2018 at a different location and angle than its sibling, offering scientists a second independent vantage point on this same transition. Because the heliosphere is not a perfect sphere, it's closer to a long, teardrop-shaped bubble, compressed on the side, facing into the interstellar wind, and stretched out into a long tail on the opposite side. The two Voyagers crossed the boundary at meaningfully different points, more than 40 degrees apart in their approach angles. Comparing their data has allowed scientists to start piecing together a genuinely three-dimensional picture of this boundary for the first time, rather than relying on a single snapshot from a single direction. Other missions, including a spacecraft called IBEX that studies the heliosphere's edge from an orbit near Earth, using a completely different detection method, and Mars orbiters like MAVEN that occasionally provide complementary data, are helping to build out this picture even further, layering different kinds of measurements on top of what the Voyagers physically experienced as they passed through. What ties all of this together, and what makes the story worth telling and retelling, is the simple fact that so much of what we now understand about the true edge of our solar system came not from prediction, not from computer simulation, but from an aging, half-broken spacecraft communicating in whispers of radio waves that take almost a full day to reach us, still surprising the scientists who built it more than 4.5 decades after it left Earth. Every model humanity built about what lay beyond the heliopause turned out to be, in some important way, incomplete. The region was supposed to be calm. It's turbulent. It was supposed to settle into a steady density. It kept climbing instead. It was supposed to be cold and empty in every meaningful sense. Instead, it contains a searing, invisible wall of plasma, tens of thousands of degrees hot, one that Voyager 1 sailed straight through and lived to tell us about, because the universe, once again, turned out to be stranger and more intricate than the equations meant to describe it. It's worth spending a moment on just how strange the very idea of an interstellar shockwave sounds the first time you hear it, because it runs against almost every intuition we carry about the vacuum of space. Most people picture the region beyond our solar system as silent and unchanging, a still ocean that never ripples. What Voyager 1 found instead was closer to weather. When that coronal mass ejection from the sun finally caught up with the spacecraft in 2013, having traveled for over a year across more than 11 billion miles, it didn't just pass by unnoticed. It slammed into the surrounding interstellar plasma and set it vibrating, the same way a struck bell keeps ringing after the mallet has already moved away. Scientists later identified several more of these events in the years that followed, each one another pulse from the sun rippling out through the boundary and disturbing the material beyond it, sometimes taking many months to fully die down. The interstellar medium, it turned out, is not disconnected from our sun's activity at all. It is still, in a very real sense, within reach of the sun's influence, still shaken by its outbursts, long after the wind itself has lost the strength to hold that territory as its own. This challenges a very old and very intuitive assumption. The idea that the heliopause functions like a hard border, a line on a map beyond which the sun simply stops mattering. The data Voyager 1 sent back suggests something closer to a permeable membrane, a boundary that solar disturbances can still cross, even if the bulk outward push of the solar wind cannot. It means the story of our solar system's edge isn't a story about a wall at all. It's a story about a gradient, a slow, uneven dynamic transition zone that stretches for a significant distance in both directions, shaped simultaneously by forces from inside our solar system and forces from the wider galaxy pressing back. Modeling that kind of gradient with any precision was essentially impossible before Voyager 1 supplied real numbers to work from. And even now, with those numbers in hand, researchers are still refining exactly how far this zone of influence extends and how it changes as the sun's 11-year cycle moves between quiet and stormy phases. There's a particular kind of scientific patience embedded in this story that deserves attention, because it says something about how real discoveries differ from the way they're often portrayed. Nothing about Voyager 1's crossing of the heliopause happened in a single dramatic instant that scientists could point to and immediately announce to the world. It unfolded in fragments, spread out over the better part of a year, pieced together after the fact from instruments never designed for this exact purpose, using an indirect measurement technique, listening to the pitch of plasma oscillations that engineers hadn't originally planned to rely on for this kind of confirmation at all. The team had to wait for nature to cooperate, for a solar storm to happen to travel in the right direction, cross the right distance, and arrive with enough strength to make the surrounding plasma detectable. It was, in a very real sense, a discovery made possible by patience and a fair amount of luck, layered on top of decades of careful engineering that kept the spacecraft's remaining instruments alive long enough to catch that moment when it finally came. Consider, too, what it actually takes to operate a spacecraft at this distance today. Commands sent from Earth take roughly 22 hours to reach Voyager 1, and any response takes another 22 hours to come back, meaning a single question and answer exchange with the spacecraft consumes the better part of 2 days. The spacecraft's transmitter broadcasts with something on the order of 20 watts of power, comparable to a dim household light bulb, and by the time that signal has spread out across 11, 12, now well over 15 billion miles, it arrives at Earth so faint that receiving it requires the massive dish antennas of NASA's Deep Space Network, arrays over 200 feet across, straining to pull a signal out of the noise that is, by the time it reaches us, a fraction of a watt. Every photograph, every plasma reading, every cosmic ray count that allowed scientists to piece together the story of the heliopause crossing had to travel across that entire gulf, arriving as the barest whisper decoded painstakingly by systems built specifically to listen for exactly this kind of faint, distant signal from humanity's most far-flung machine. There is something profoundly humbling in that. We spent decades building theoretical frameworks for a place none of us could visit, refining equations based on the best physics available, confident that we understood, at least in broad strokes, what the transition from our solar neighborhood into true interstellar space would look like. And then a machine, older than most of the scientists currently analyzing its data, flew through that transition and revealed that reality had its own ideas. The plasma didn't behave the way the models said. The temperatures didn't match expectations. The boundary itself turned out to be less like a wall and more like a living membrane, breathing in and out with the rhythms of a star 93 million miles away and the pressure of a galaxy far beyond it. Voyager 1's discoveries at the edge of the solar system are a reminder that exploration, real exploration, the kind that sends an object further from home than anything has ever traveled, will always outpace our ability to predict what it will find. No amount of modeling, no matter how sophisticated, can fully substitute for the simple act of going there and measuring what's actually present. That has been true throughout the history of science, but rarely has it been demonstrated so vividly, so dramatically, as it was when a spacecraft the size of a small car, carrying instruments designed in the era of vacuum tubes and punch cards, radioed back data suggesting the edge of our solar system was hotter, denser, and stranger than anyone had dared to predict. As Voyager 1 continues its silent journey outward, its power slowly fading, its instruments being switched off one by one in a carefully managed act of engineering triage, it carries with it not just the golden record and the hopes of the scientists who built it, but also a body of data that will occupy researchers for decades to come. Every new theory about the shape of the heliosphere, every future mission proposed to follow in Voyager's path with sharper instruments and greater precision, will be built on the foundation this single spacecraft laid down, almost by accident, as it stumbled through a wall of fire nobody expected to find at the edge of everything we call home. And somewhere out there, more than 15 billion miles away and climbing, still transmitting, still listening, still surprising us, Voyager 1 keeps moving, carrying humanity's questions further into the dark than they have ever gone before, and bringing back answers stranger than anyone imagined possible.